Okay, having seen the finite representation of language in the last video, the architecture of it, let's begin with the deterministic finite automata now. So, what is deterministic? For every possible combination of a state and symbol, for example, what are the possible combination of state and symbol in this for this DFA is Q0A, Q1A, Q2A, Q0B, Q1B, Q2B. So these are all the possible combination of state and symbol, and this is the basically the configuration of a DFA. So for every possible combination, you must have a move defined. You must have the logic for state transition, and that logic is going to be unique. That is why it is deterministic. From a given state, on reading any symbol, it will go to unique state only. Unique state. So Q0 on seeing an A will go to one and only one state. It will first of all, it must have a move defined, and second, this move has to be unique. So Q0 on A will go to Q1 only. There is no more than one move defined for a combination. For any combination, there is only one unique move that is defined, and that is why it is called deterministic. There is a consequence of this determinism that we will look in a little while. So Q1 on seeing A will go to Q2. On B it will go to Q2 also. And Q2 on seeing A, it will stay at Q2 itself. And when the machine is in the state Q2, if the input symbol is B, then it will go to Q0 state. There is one thing missing here. There are two more things in the deterministic finite automata, that is, there is going to be one initial state. There is going to be one initial state. So Q0 is the initial state. What we mean by initial state is that from this state you will start to scan the string. So you will before you see the first symbol, at what state you are in, that is your initial state. Okay, so there has to be some starting point, and that is what the initial state is. And there is one more thing, which is the final state. Final state. So out of these many states, there will be one or more than one final states. What does this mean? This means that final state, we will see that if your string, if you completely scan the string from the left to the right, and if you end up in the final state, then you will say that your string is a part of the language. Okay. Because of this determinism, for every string, we will end up at a unique state when starting from the start state. Let's say this is your string AB, A, B. This is your string AB, A, B. So what is, it will always take a unique path because the moves are fixed. It will always take the unique path because the moves are fixed. Let me take a new page and explain it. For this string AB, AB, we will see that every time this will follow a unique path. Every string will follow a unique path. This is something that you have to note. Make a note of it. Every string will follow a unique path. Will follow a unique path. Okay, so you are the input head is, tape head is pointing to A, and initially you are at state Q0. So Q0 on seeing A will go to which state? Q0 on A will go to Q1, and Q1 at B will go to Q2. So tape head is every time the state transition happens, the tape head moves one step to the right. So now you are at Q1, DFA machine is at Q1, the tape head points to B, so it goes to Q2. Q2 on seeing A will stay at Q2. It will stay at Q2. Again, on seeing A, it will stay at Q2. And on seeing B, Q2 on seeing B will go to Q0. So this is what will happen every time. Anytime you give this string to the machine, it will follow the same path, because there is no two ways about the moves. The moves are unique. From Q0 on seeing A, you will always go to Q1. Okay, and that is what we call as determinism. And it is because of this determinism. So every string will follow a unique path because of determinism. Because of determinism. Okay. If you see, this is your length of the string A, B, A, A, B. What is the length of input string? What is the length of input string? The length of input string is 5. Means what is the length of the sequence of states? Q0, Q1, Q2, 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 Q0. 1, 2, 3, 4, 5, 6. So the length of sequence of states, is equal to 6. So in a deterministic finite automata, every time whatever your input string length is, your length of sequence of state will be one more than that, because you are starting from a initial state without seeing any input. So the sequence of state includes that initial state. So it is going to be one more than the length of the input string. This is information that we will capitalize later on. Because every string follows a unique path, it means given a fixed start state, every string will always ends up at a fixed particular state. At a fixed particular state. We can say this. For example, this ABAAB, this string, if it starts with Q0, it will always end up at Q0. Similarly, if you take another example of a string, let's say we take ABA, this string, ABA. If this string starts from Q0, it will always end up at Q2. How? So simple. ABA, initially it is at Q0. Q0 on seeing A, it will go to Q1. Q1 on seeing B, go to Q2. And Q2 on seeing A stays at Q2. So this path, every time ABA is fed to the machine and the start symbol is Q0, then every time this ABA will end up at state Q2. That's what it is. Given a fixed start state, every string will always ends up at a fixed particular state. We can say that the set consisting of all the strings can be partitioned based on the states they will end up. So for this example, for this DFA, let's say if this is a set that contains all the strings possible over an alphabet, it contains all those strings possible over an alphabet. So P0 represents with those strings which will always end up at Q0. If we start scanning from Q0, it will always end up at Q0. Similarly, P1 consists of all those strings. When we fed it to the finite automata, it will always end up at Q1. And then let's say that the P2 partition contains all those strings that will end up at Q2 if these strings are fed to the finite automata. So we can think that set of all strings has been partitioned corresponding to the states of the DFA. So each state basically corresponds to all those strings that ends up at that particular state. So we can think of DFA like this. And if you remember, the final moments in the previous video, I said that you design a DFA in a way that each state means you being at any state after traversing some part of the string, if you being at one of the state conforms the kind of a pattern that you have traversed in the string. So this is what it is. So when you P0 corresponds to all those strings that will end up at Q0 always. P1 corresponds to all those strings that will end up at Q1 always. P2 corresponds to all those strings that will end up at Q2 always. Now there is another thing called as string accepted by DFA and language accepted by DFA. In DFA, there are one or more final states, and the strings, all those strings that ends up to one of the final states are said to be accepted by DFA. So if Q2, let's say, is the final state, then all those strings under P2, we will say that the strings under P2 will be accepted by the DFA. Okay. Starting from initial state, if string S ends up in one of the final state, we say S is accepted. We say S is accepted by DFA. And what is the language accepted by DFA? What is the language accepted by DFA? Okay. So DFA accepts a language L if every string in L is accepted by M and no other string is accepted by DFA. So if there is a language and the language consists of all those strings, okay, in simple terms, in very simple terms, if the language is equal to P2, this is the language accepted by DFA. So in simple language, this L, the language of the DFA, the language accepted by DFA or the language recognized by DFA, in simple language, that is P2. It is P2. So this is the language recognized by DFA. That is what we will see in that slide. So if every string in, okay, what is the language of the DFA? If all those strings which will end up in the final states of DFA, all those strings which will end up in the final states of DFA are the elements in any language and there are no other strings in the language, then that is what language of the DFA is. So if your DFA, let's say, have 5 states and Q3, Q4, Q5, these are final states. These are the final states. Then just we saw that the set of all strings, set consisting of all the strings, will be partitioned. Let's say this is partitioned in S1, S2, S3, S4, S5. S1 consists of all the strings that ends up at Q1, S2 all strings that ends up at Q2, S3 all strings that ends up at Q3, and S4 to be, let's say S4 to be the set of all strings that ends up at Q4, and S5 is set of all strings that ends up at Q5. The language of the DFA will be S3 union S4 union S5. S3 union S4 union S5, because these are the strings that will end up in the final state. So every DFA has a language associated with it, referred as language of M. So this is also a point, that every DFA is associated with one language. Every DFA is associated with one language only. With one language. Every DFA is associated with one language. For every DFA. So let's say if the DFA is for DFA M, what is that language? This is that language. Okay. So language of M is equal to S3 union S4 union S5. This is the language. So this language should contain all the strings that will end up in S3, S4, S5. If this language has any string, if this language, let's say if this language is one string short, even one string short, then this language will not be considered as the language of the DFA. So out of S3, S4, S5, let's suppose AB is also a part of any one of this partition, and your any language L1 does not have AB only, rest all of the strings are there in the language, then still this L1 is not LM, is not the language that is recognized by DFA. A language recognized by DFA would be such a language that has all those strings that will end up in the final state, and apart from these strings, no other strings. This is very important. No other strings. So let's say that in S3 partition, S4 partition, S5 partition, AAB is not any of the element. AAB is not to be found in any of this partition, and your L2 is S3 union S4 union S5 union AAB. So even if it has one string which is apart from these strings, then L2 is not the language of the DFA. So the language of DFA is strictly, number one, that it has all those strings that will end up in the final state, and number two, apart from that, no other strings. No other strings. So you have a fixed language. Every DFA is recognized by a language. So when you look at, when we can say like this, if a DFA is given, you can ask what is the language of the DFA. Okay. If a DFA is given, you can ask what the language of the DFA is. And as we know, the main purpose of any automata is to solve the set membership problem. So the DFA solves the set membership problem of this language. Means DFA recognizes some language, and it is this language that DFA solves the set membership problem mechanistically. Okay, that's it in this video, and we will look at examples of DFA from the next video. Thank you very much.